Hey guys, welcome back to the Maths Made Easy series. This is the series where we go through each of the topics and we start from the basics and we work our way through to the really hard style questions. Now, I will point out that you will have to do some of your own reading or learning in order to fully understand what we're doing here, but this is aimed to try and get you all the way up to that grade A or A star style of question. Just so you know, with this differentiation, we're doing things in year 12, so things like proving things from first principles, stationary points, that kind of thing. Also, modelling with differentiation is actually a separate video because that is a huge topic with a ton of really hard questions. That'll probably be the next video or the one after that. So this one is just going through the more basics of the differentiation, and then right at the end there's actually a pretty tricky question. That was 9 marks in total, which is a pretty fat number of marks. As usual, I'm going to put a link in the description for all of these questions plus the notes, so that way you can retry them whenever you want and you can look at the notes and all that wonderful stuff. Without further ado, let's jump into what differentiation actually is. So from first principles, differentiation simply is a way of calculating a gradient. Now you might think, well, why the hell would we need that when we already have, the good old-fashioned change in y over change in x? Well, that really only works for straight lines. But if I have a curve, for instance, and I ask you to work out the gradient over here, you have to do something like drawing a tangent. But the thing is, the tangent can be multiple different things. Like this, I might say that's a good tangent, but you might say, no, it needs to be a bit more steep. And honestly, who's to tell who's right? If you remember in GCSE when we did kind of equations of tangents and working the gradients out, you got a variety of answers, right? A range, which isn't really good enough in maths. Differentiation is a way of eliminating that and finding an actual equation for the gradient. You might think, why do we get an equation? Well, simply put, can you see that the gradient will change along this entire curve here? It goes from a negative value down to 0 and then to a positive value. It changes all the time, which means it won't just be a number. The gradient isn't 5, for instance. It's different. This might be -4, then it goes down to 0, then it goes up to +4, something like that, and all the values in between. So we actually need to get an equation. So let's start off with how the gradient is actually defined in terms of differentiation. The very first thing you're expected to be able to do is to prove from first principles that the derivative of kx cubed is 3kx squared. I decided to start with this because you don't actually need to know differentiation to know that this is true. So differentiation relies on drawing tangents but making them infinitely small and precise, which means we do it mathematically, we do it algebraically, so they are 100% accurate. And here is how differentiation is labelled. It is considered as the limit as h tends to 0, I'll explain what the limit is in a second, of f of x plus h minus f of x, all over h. So we sub in these values, we simplify it, and then we make h equal to 0. The common mistake I see students make is they try and make h equal to 0 too quickly. If I make h equals 0 right now, I'll get a math error because I'm dividing by 0. That is not what you're supposed to do. You're supposed to substitute this all in first, do all of the algebra, simplify it, and then when you can't simplify it anymore, then you make h equal to 0. That's what this limit thing means. It means that if I make h 0, what happens to the expression? So first of all, let's define what f of x is. F of x in this case is going to be kx cubed. I would like to point out that I have picked a hard question, so it's probably the hardest that you'll get in year 12 for proving from first principles. That means f of x plus h, well, all I do is I replace x with x plus h. So we get k x plus h all cubed. And then of course h is just h. Let's sub this in now. I'm going to stop writing the limit, although that isn't super accurate. I'm going to stop writing the limit just so we can do the simplification first. So we have k x plus h cubed minus, in fact that should be, so again, technically speaking, the x cubed is the only thing being cubed. The k is not being cubed in this case, just so you can see that kind of a bit more clearly. Minus kx cubed over h. So again, that point that I just made, make sure you know what's being cubed. It's the x, it's not the k. That's why it's only the x plus h being cubed here. Next thing we need to do is we need to expand the brackets and simplify. I'm going to point out this is a bit annoying, but again, part of A-level maths is doing some pretty annoying algebra. So the way I would do it is I would expand two brackets first. So if you remember, x plus h cubed is going to look like this. So if I expand just two brackets first, I will get x squared plus 2hx plus h squared. And then I'm still timesing by x plus h because I haven't done that yet. Minus kx cubed over h. I do want to also point out that these questions are generally 4 marks. So it's a very basic algebra, so take your time with it. Every time I mark year 12 assessments, a good chunk of people will make mistakes in the algebra and not get the answer. And then they spend time panicking, wondering why they haven't got 3kx squared. Don't be one of those people. Take your time. Be slow and methodical. So, here we're still going to leave the k on the outside. We have x squared times x, which is x cubed. X squared times h, which is hx squared. Then we have 2hx times x, which is 2h x squared, plus 2h squared x, plus h squared x, plus h cubed. Close bracket minus kx cubed. I know this seems like a lot, but I promise we're going to start simplifying it now. Over h. Then what I'm going to do is I'm going to expand the bracket, as in the k bracket, but I'm also going to, gather like terms. So we have x cubed times k. There's no other x cubes here, so that's just kx cubed. Then if we gather up the hx squareds, we have hx squared plus 2h x squared, and that's it. So that gives me 3hx squared times k. So that's 3k hx squared. Then we have h squared x, so that's 3h squared x times k, so that's plus 3k h squared x. And then lastly we have h cubed, so we have kh cubed, yes. I know. This looks very fun, I know. Over h. Hello, over. Cool. The kx cubed and minus kx cubed cancel. Now if I do the division, what am I left with? I'm left with, well, again, if we cancel, h cancels, h cancels, h cancels. So we're left with 3kx squared plus 3khx plus kh squared. Okay, now we go back to the limit. So the limit as h tends to 0. So let me move this over slightly. Again, it's a 4-mark question. The lim as h tends to 0. Well, if I have a look at this entire expression, if I make h equals 0, the first thing will stay exactly the same. So I'll still be left with 3kx squared, but the khx, that'll be 3k times 0, so that goes away. K times 0 squared goes away. So I'm left with 3kx squared, which is our answer. Now some people like to try and be dodgy and they try and expand this and then write therefore equals this. You need to show the intermediate steps. Okay? You can't just wishy-washy jump to the end, okay? So now we've seen what first principles are, and again they can ask you to do all kinds of differentiation with that. Let's actually look at what differentiation is and how we use it. So here we have an equation of a cubic, so 2x cubed plus 5x squared minus 7x plus 10. Find dy by dx. This means here, if you remember, to work out the gradient it was the difference in y over the difference in x. You can think of it as dy as being difference in y over difference in x. All it means is the equation for the gradient, or it means you're doing differentiation. That's all it means. But how do you actually differentiate something? Well, all you do, and I'm going to show you right now, using part A as an example, is you bring the power to the front and reduce the power by 1. So, bring the power to the front, we have 2 times 3, which is 6, x to the power of 2. Let's move on. Bring the power to the front. So that becomes 5 times 2, so 10, x. Now, let me show you how this technically works, right? If you give yourself anything, for example, x cubed, if you differentiate it, you would get 3x squared. In general, this is how it works. If y is equal to ax to the power of n, then dy by dx is simply an x to the n minus 1. That's it. Now you might be thinking, what about this? What about x? Well, x is technically to the power of 1. So that becomes minus 7x to the power of 0. But what is anything to the power of 0? It's 1. So it just becomes minus 7. If you differentiate anything that is not a constant, but if it's just linear, if it just has a power of 1, you just get rid of the x. That's all that happens because it becomes x to the power of 0. What about 10 though? Because 10 doesn't have a power of x. Well, here's the way it works. We look for the difference in y with respect to the difference in x. So basically, how much does this equation change every time I change x? So for example, 2x cubed, if I vary x, will vary as if it's 6x squared. 5x squared varies as if it's 10x. 7x varies like 7. Well, does that make sense? If I drew a line which is y is equal to minus 7x, it would be a linear, it would be a constant gradient going downwards. What about y equals 10? That's a flat line, there's no gradient. Constants will always go to 0 when you differentiate them because they don't change, they have no gradient. The gradient of 2x cubed is 6x squared, 5x squared is 10x, minus 7x is minus 7, the gradient of 10 is nothing because it doesn't change. It is a flat horizontal line. Whereas the 7x thing, well, if you drew the graph of minus 7x, it's a straight line going downwards, right? It's a diagonally downwards graph. So the gradient would just be minus 7. Okay, then what about part B? This is where differentiation gets really, really, really useful. Find the gradient of the curve when x equals 2. This here is an equation for my gradient. If I sub in x equals 2 into the equation for dy by dx, it gives me the gradient of the curve precisely at that x coordinate. How cool is that? You don't need to use tangents. You don't need to use any kind of approximations or estimations. It gives me the exact gradient. So that would become 6 times 2 squared plus 10 times 2 minus 7. And whatever that is my answer. Again, all of A levels is calculator, so you can just start using a calculator for this. Very nice and easy. Assuming I can click the buttons anyway. 37. So the gradient at that point is 37. Again, no tangents drawn, no estimations, no approximations. That is the exact gradient at x equals 2. That is the power of differentiation. You don't have to estimate anything. Very useful. So let's try it one more time, but with a different equation. If you notice, we have this 1 over x. You don't know how to differentiate 1 over x yet, so we're going to rewrite this. Again, I'm assuming you've done my indices video, and I hope you have, or at least you've learned it in school, but you can write that as x to the power of minus 1, where we do the same thing with dy by dx. Okay, so that, remember, that's 3x to the power of 1. Bring the 1 forward, so that's 3. Actually, I should write dy by dx first, got a bit too excited. X to the power of 0, which is 1, so we don't need to write it. This one is interesting though. Bring the power forward, we get minus 1. Then we get x, and what happens when I subtract 1 from that? I get to the minus 2, which you can either write as minus 1 over x squared, you can write it as minus x to the minus 2, however you want, but that's the answer. Cool. Now, part B, again, is where differentiation gets a bit more interesting. Now, if you imagine a curve, for most of a curve, the gradient has some value, positive, negative, whatever. The interesting parts of a curve is when the gradient is equal to 0. These are called stationary points. So either you call them stationary or you call them turning points. The reason for that is, well, if I show you, if I draw a cheeky little quadratic, the point where the gradient equals to 0 is that point right there. Why? Because if you look before, the gradient is negative, right? the gradient is negative before this value, and the gradient is positive afterwards, which means at some point between being minus and being positive, it must be 0. Okay? And you can also do it the same way with a reverse quadratic, so something like this. Starts off positive, and it becomes negative, which means somewhere in between it must have a gradient of 0. That's the interesting point. That's why they call it a turning point. They also call it a stationary point because the idea there is the gradient's not moving, there's no gradient at all. Those are the interesting points. I mean, how would you do that? Well, think about it. Where the gradient is equal to 0, find the x coordinates. Okay. Well, this is my equation for the gradient, right? So if I'm looking for when the gradient is 0, I just sub in that the gradient equals 0. And then I solve it. Okay. So I'm going to move the negative x over to the other side. So we'll get 3 is equal to x to the minus 2. It might be beneficial now to actually write this in terms of a fraction. So I'm going to times both sides by x squared. We get 3x squared equals 1. So we get x squared equals a third. Square root both sides and we get x equal to square root a third. But remember, when we square root now, it's plus or minus. Because, look at this, it's plural. It means there's more than one x value we're looking for. So you will lose marks if you don't have plus or minus, because that means you've only found one value, you haven't found 2. There's 2 values for this one. There are 2 turning points in this equation right here. So again, keep this in mind, because it is a very useful and important thing. And we're going to also go through, how do we know if it's a kind of a this shape or a this shape? It's a good question. Ta-da. Okay, so the curve has the equation y equals 2x cubed plus 9x squared minus 24x plus 13. Very long equation. Find the coordinates of the curve's local maximum. So in the previous question we spoke about turning points. So we have 3 different turning points. Now I'm actually going to draw them without axes just to make it a little clearer. We can have a point like this where we go from a negative gradient to a positive gradient. That is called a local minima. Minima. There we are. Minima. That is an M, believe it or not. It's not 2 separate N's. We can also have something that goes not like that at all. That goes from a positive to a negative. And this right here is called a maxima. If you want, you can... So basically the plural of maximum is maxima. The plural of minimum is minima. That's where those fancy words come from. I'm really not happy with how that M turned out. So, minima. But there's one other possibility, right? We've gone from negative to positive, positive to negative. But what if it goes from negative to negative or positive to positive? What if it stays the same? So something that either looks like this, or where if we look at the point in the middle, it's negative to negative or positive to positive. That is called, there's 2 ways to call it. I call it the point of inflection. Some people call it a saddle point, which actually isn't mathematically correct. A saddle point has to be 3-dimensional. This is only a 2D, so it's a point of inflection. But how can you tell? Right? How can you tell which one's which? Because before, we just made the gradient equal to 0. How do I know if this is a maxima, minima point of inflection? This is where things get interesting. We have to differentiate again. So, it looks like this when we differentiate twice. We sometimes call it a second order differential. I just like to say double differentiating because it sounds cool, I guess. Cool, is that the right word? Probably not. So how do we know if it's a minima, maxima point of inflection? Now here's where people get confused. This second differentiation is going to tell me how the gradient is changing. I like to think of it as acceleration. So in maths and physics, when you have velocity, it's how quickly your distance is changing. Your acceleration is how quickly your velocity is changing. You can have a positive velocity and a negative acceleration, right? Because you could be slowing down. That's the kind of idea here. Can you see my gradient is going from a minus to a positive? So the change in the gradient is positive because there's a positive change in the gradient. It goes from minus to positive. That means overall it's a positive change in the gradient. Hope that makes sense. So if my second order differential, my double differential, is bigger than 0, it is a minima. Maxima, it goes from a positive to a negative, so the change is negative. So that means the double differential, or the second order differential, is negative. Because it's, again, if I was speaking in terms of velocity, it's slowing down. Whereas this one, it's speeding up. Point of inflection, well, it goes from negative to negative, there's no change. And here it goes positive to positive, there's no change. So it equals 0. So what are we going to do here? This is a beautiful question. It is a 6 marker, but in my opinion, it's a really good 6 marker. You're going to differentiate. So the first thing we're going to do is differentiate this. If you are feeling a bit brave, I'd like you to pause the video now and actually have a go. Bring the power forward. We get 6x minus 1 from the power, so 6x squared. Bring the power forward, that's 18x minus 1 from the power. Basically, just get rid of the x, it's minus 24. And the constant on the end goes away because it's not changing with respect to x. There's no change, doesn't affect it. Cool. Now, just like in this previous question, to find the coordinates where the gradient is 0, that will give me the x coordinates of my stationary points. Not necessarily the maximum. The maximum will be one of them, but there may also be a minima or a point of inflection. Maybe there's 2 maxima, who knows. But to get my x coordinates, I'm going to make this equal to 0 and solve it. And here's the beautiful thing about A-level maths. You can solve this in whatever way you want. You can try and factorize, although I wouldn't waste my time because maybe you can't factorize this, right? Maybe you can't. No point wasting your time. I would use the quadratic formula or the calculator. So on your calculator, menu, down twice to the right, equation / func. Polynomial just means something with x in it, basically. X to the 1, x squared, x cubed, whatever. The degree is just the biggest power, which is squared. Then we just type in our values. People do ask me, can you get marks for this? The answer is absolutely, because they're not actually testing if you know how to solve a quadratic. That's not the point of the question. It's part of it. So I have 2 x coordinates. We have x equals 1, and we have x equals minus 4. Okay, now which one, if any, is the maximum? Don't know. How can I check? I differentiate again. So we're going to do our second order differential, our double differential. How do you differentiate twice? You do the same thing again. Power forward, 12x. And remove 1 from the power, plus 18. And now, what I'm going to do is I'm going to sub both of these values in and see which one gives me, for a maxima, a negative answer. So here we go. D squared y by dx squared will equal 12. You might be able to see already which one's going to give me a positive and negative. But that's going to give me 12 plus 18 is 30. That's bigger than 0, which means it's a minima. So it's not that one. Same thing with this one. Can you use your brain to kind of predict which one it is? Absolutely, of course you can. 12 times minus 4 plus 18. So it's minus 48 plus 18, which is minus 30. Yeah? It's less than 0, which is the maxima. That's the one I want. Am I done? No. Read the question. I would have gotten 5 out of 6 if I stopped here. Find the coordinates. I've only found an x coordinate. How do I find the y coordinate? Funnily enough, this is actually where students get very confused. Is finding the y coordinate. They're like, oh, do I sub it into dy by dx? No, because you'll get 0, right? That's the point. Do I sub it into d squared y by dx squared? We've already done that. That's not the y coordinate. You sub it into the original. So, here's the problem with differentiation at A level, especially year 12. Which equation do I sub it into is the most common question I get. Here's how you know. If it's the equation for y, that is only for coordinates. So if they ever ask you about finding the coordinates, you're subbing into y. dy by dx, that is when you want the gradient, or turning points, TP, or stationary points. It's the only times you're going to use that. For d squared y by dx squared, you only need it if you want to verify which turning point a coordinate is. Okay? So, one more time. If you ever want a coordinate, now you might be thinking, well, hang on a minute, it says find the coordinates, or back here it said find the x coordinates. I'm talking about if you want the whole coordinate, you're going to be subbing back into the original. If you want the gradient, or the turning point, or the stationary point, or where the gradient is 0, whatever, that's dy by dx. If you want to verify, so d squared y by dx squared is quite rare. It's only if you want to verify which turning point a coordinate is. Is it a maxima, minima, point of inflection? That's the only time you use d squared y by dx squared. So subbing into the original equation, we can get our y value to, this might take a bit of time, plus 9 4 squared. I'm just going to put it like that. I can't remember if it's minus or plus. Minus 24. Plus 13. Yeah, good. Find that value, and this is going to be our y value. Again, go to menu, go back to the top. So 2 times 4 cubed plus 9 4 squared minus 24 4 plus 13 gives me 189. That's my y coordinate. And for the very last thing, I would literally write minus 4 189, and I'd even put it in a box so that way the examiner has no excuse. That is a 6-mark question, and look at it. Like, this top thing is notes. We did 1 line, 2, 3, 4, 5, 6 lines, 6 marks. But look at the actual maths. The actual maths we did. Differentiation you're going to find pretty easy eventually. Subbing in numbers into a calculator, solving quadratics, that's not bad. The difficulty is knowing what to sub in and where. The other difficulty, and I'd say this is probably the biggest difficulty, is you guys write your working out horribly. Lay it out neatly. You know, make it nice and logical, like you're trying to explain it to someone. Because I promise you, if it doesn't make sense to the examiner, it probably didn't make sense to you. You probably would have made some mistakes. Write it out neatly and your life will be 10 times easier. This leads us to the natural... Well, I mean, it's one of the 2 tricky questions I really put in here. And the good news is this one is actually super, super, super common. And once you know it once, you really know it every single time it comes up. So here we have a curve with an equation. And it says to find the equation of the tangent to the curve at the point 2, 13. They can also ask for the normal. But there is literally only one tiny difference between a normal and a tangent. So the key thing here is that when you have a curve and a tangent, the tangent at that point will have the exact same gradient as the curve. So remember, to get a tangent, you need y equals mx plus c. You need to have a coordinate to work out c, and you need to have a gradient. So we're going to differentiate this curve and sub in the x coordinate of 2 to find the gradient at that point, which is the gradient of the line, and then sub in the coordinate to find what c is. That's it for 5 marks. So differentiating once gives us 6x squared minus 4. So then at x equals 2, our dy by dx will equal 6 times 2 squared minus 4. So 2 squared is 4 times 6 is 24 minus 4 is 20. That's it. So what's the difference between the tangent and the normal question? Well, this is the only difference. With a tangent, our m is going to be the exact same value as the dy by dx. With the normal, we would have to do the the negative reciprocal. That's it. So if they give you a normal instead of a tangent, it's the same thing, the same process. You're just taking the negative reciprocal of the gradient, and that's it. So now we have y equals 20x plus c. So to work out what c is, because remember we do need to work it out, we're just going to sub in these coordinates. That's it, we're done. So x equals 2, y equals 13, based on those coordinates, right? 2 and 13. So we have 13 equals 20 times 2 plus c. So that's 13 equals 40 plus c. So that means minus 40 from both sides, you get what, 27? Negative 27? Yep. So then our answer is just y is equal to 20x minus 27. For 5 marks, I think that's really, really good. Again, the only difference if it's a normal is you take the negative reciprocal of that m value, and that's it. That's really as hard as it can get. They can get you to do it with circles as well, but remember, you just differentiate. It's the same type of thing, right? So with any curve, you differentiate and sub in whatever the coordinates are. Let's move on to the hardest question. It's a pretty tricky one that came up in recent years. Here is the question, and in my opinion, it is one of the trickiest questions that's come up, but not really as well. And the reason why I say that is it's tricky for A-level students in year 12 because they don't know you're allowed to do this, right? And that's the biggest difference between GCSE and A-level, is the problem solving that you have to do. The maths is going to be just as easy as it's been so far, right? So if you found it hard, it'll be hard. If you found it easy, it's going to be easy. The difference is how we're going to use the information. And remember what I always say in my catchphrase in GCSE. They have to give you enough information to do the question, and they will never give you information you don't need. So in this case, each of these things is useful. Now, it tells me that g of x is a cubic. The general equation for a cubic will be something with x cubed, something with x squared, something with x, and then a constant on the end. But remember, we don't know what the numbers are in front of x cubed, x squared, x, or on the end. So that's my first step. But now it says it's cubic in which the coefficient of x cubed is equal to the coefficient of x. So in other words, both of those values are the same. So I'm going to say it's ax cubed plus bx squared plus ax plus d. That's what that is. So I've used that first piece of information. The next thing is that it passes through the origin. That means that when x equals 0, y should equal 0. So if I sub that in, we get 0 equals a 0 cubed. Honestly, you probably worked out what this is already, but I'm just being super thorough. Plus d. So in other words, all of these are 0, so d is just equal to 0. So now we have y equals ax cubed plus bx squared plus ax. That's it. Now we've used that last piece of information there. You see what we're doing here? We're just using all the information they give me in order to work things out. Now this third bullet point is actually where a lot of students get confused, because it looks like one piece of information, but it's not. It's two pieces of information. First of all, it tells me there's a stationary point at x equals 2. Okay, stationary point means I differentiate, so let's differentiate this. 3ax squared plus 2bx plus a. And it tells me there's a stationary point at x equals 2. What does that mean? It means at x equals 2, dy by dx should equal 0. Oops. So that means we have 3a2 squared plus 2b2 plus a should equal 0. So if we expand this now, we have 2 squared is 4 times 3 is 12. So 12a, but plus another a, so it's 13a plus 4b equals 0. And this is where people get to and they're like, I don't know what to do now. There's a hidden piece of information they've given you. They've given you a coordinate. So in other words, when x equals 2, y equals 9. There's actually two pieces of information in that one line. Very devious. They could have said, has a stationary point at x equals 2, and then said, the coordinate 2, 9 lies on the curve. But instead they made it a bit harder by putting two pieces of information in the same line. That's why this was a very hard question. So if I sub that in now, we have y is equal, well, we don't have, we have 9 equals. Actually, no, let's sub it in from left to right like we were doing here. So a2 cubed plus b 2 squared. If you're unsure what I'm doing, I'm subbing in x and y into this equation, but I'm going to put y on the other side, just to make it a bit more, well, I'm just doing it, equals 9. If we simplify, so 2 cubed is 8, so we have 8a plus 2a, so it's 10a, plus 4b equals 9. Yeah, that is correct. Cool. Equals 9. So now we have two equations, two unknowns. What do? We do simultaneous equations. So if I write them on top of each other, I was going to drag them over, but I realize you guys can't do that on paper, so let's do it like this instead. I would just subtract them. 13a minus 10a is just 3a. 4b minus 4b is 0. Minus 9, so a is equal to minus 3. Sub that into, which equation would be good? I mean, either one's probably going to be fine. I would sub it into the original just so there's a little less rearranging. So 13a, so it's 13 times minus 3, minus 39, plus 4b equals 0. 4b equals 39. So b is equal to 39 over 4. Now remember, we need to actually find the entire equation, I believe the question actually says. Find g of x, and now we're going to sub in all of our values. So g of x equals, there was minus 3x cubed, because remember we worked out what a is. This is our equation here. Plus b, so it's plus 39 over 4, x squared. And then we have plus ax, so it's minus 3x. Job done. For 7 marks is actually not that bad, all things considered. By the way, they can give you up to 10 mark questions in A-level now. But again, I think the hardest part, or at least it's noticing it that's the problem, is definitely the third bullet point. Not easy. Part B, prove that the stationary point is the maximum. Well, this is quite nice because we've already worked out what dy by dx is. All we need to do is do d squared y by dx squared. So, in fact, I'm going to write it in terms of a, b, and x. Sorry, a and b. So we're going to have 6ax plus 2b. Then I'm going to sub in the values we worked out. So a was minus 3. So 6 times minus 3 is minus 18x. 2b, 2 times 39 over 4 will give you 39 over 2, but you're more than welcome to check that out. And then prove it's a maximum. Well, the x coordinate was 2. So when x equals 2, d squared y by dx squared. Again, I would recommend always writing out the substitution. Equals, and let's work it out. Again, I know it's negative, but I like to just be really thorough in my answers. Oops. Minus 18 multiplied by 2 plus 39 over 2 gives me minus 33 over 2. That is less than 0. And remember the reasoning from before. It means it's a maximum because we're going from a positive gradient to a negative gradient. So overall, the change in the gradient is negative. Change in gradient is d squared y by dx squared. That brings us to the end of the standard differentiation, as I'm going to call it. Then in the next couple of videos, we're going to be doing the modeling with differentiation, which is where it gets honestly pretty spicy because there's so many different situations they can put you in and they are very tricky. But of course, we're going to go through every single A-level topic eventually. That includes the applied stuff, so stats and mechanics. That should be very fun. Again, I'll give you the link to all of the notes and stuff in the description. It's on Patreon, but remember, it's free. So you don't have to pay for it. It's just that's where I host it because it just happened to be the most convenient thing for me. But I hope you have a wonderful day and I'll see you in the next one.